Okay, so welcome to our second lecture on related rates, where what we're going to do is we are going to just do some examples. Okay, now it's very important in these questions to, I would say, slow down, read the question, and don't make any fast moves. Okay, so let's see. We'll read the question, maybe we'll just read it through first. We'll see what comes up. So consider water flowing into a large upturned cone. Presumably upturned cone means something like this. I should know, I did write this question. Anyway, such that the ratio of radius to height is 1 to 2. So in a cone, you've got the perpendicular height and the radius, and in this one, the height is twice as large as the radius. Then, if the height of liquid in the cone is h, it can be shown that the volume of liquid in the cone is this. So that would just be I'll just explain where this might come from. So the radius of, the ratio of radius to height is 1 to 2. That means the height is twice as large as the radius, and the radius is equal to the height divided by 2. And then the formula for the volume of a cone is 1/3 pi or squared h. But here we have a relationship between the radius and the height. The radius is the height over 2. If you square this, height over 2 by height over 2, you get height squared over 4. So you get 1/3 pi height squared over 4. Height squared by height gives you height cubed, and 1/3 by 1/4 gives you the 1/12. Okay. Suppose the water is flowing into the cone at a rate of 0.05 cubic meters per second. Okay. Now, what we have to see is water flowing in. This is a change in volume. So this is equal to dV dt. This is the rate of change of volume. Water flowing in is going to increase the volume of water. Find how fast the height of the liquid. Now, so it says that this is the volume of the liquid. It actually doesn't say how high the cone is. So basically you've got water going in, and it's getting, the water level is getting higher and higher. Now, why these questions aren't really easy, by the way, is that the rate of change of height changes because initially, like it's like a funnel, it actually kind of, the height increases quickly as, there's not much volume to take up here. But as you get higher and higher up, to get, say, go 1 centimeter higher, you need more and more volume. Because what you have actually is that the suppose the cross-sectional area is increasing with time. This is what we're talking about. Anyway, so this is dV dt, the rate of change of volume with respect to time. Next thing is find how fast the height of the liquid is changing. So how fast the height is changing, that's the rate of change of height. That is what the question is about, dH dt. This is what we're interested in. Well, yeah. Okay, so what we have to do here is, as we saw in the previous lecture, we have to identify what are the variables. And here we have volume, height. Now you could bring in radius, but it's not really mentioned. It's just basically not there. Just forget about it, I would say. I mean, if you look, it's all about height, and the question has already written the volume of liquid in terms of height, so we don't have to do it. And then the other thing, of course, is time. Now, what you should do then, what I recommended in the previous lecture, is you take the most complicated thing. And what complicated means is that if something is a function of something else in a kind of a natural way, so volume is a function of height, then the volume is the complicated thing. Height is kind of primitive. So you differentiate the complicated thing, which is V, with respect to T. And what we said in the previous lecture is you can do this kind of maneuver. It's kind of nonsense, but it does give you the right answer. dV dt. And then you bring in the other variable, which is dH. Now, well, h is the other variable, but you put in dH and dH. Now, doing this is nonsense, but it does give you the right answer. Well, now that it's written, it's not nonsense. It's the chain rule. Okay, so the question says, the notes here. So we know what dV dt is. The question is, can we calculate dVdh? Now, something that we're going to set up for next week's lectures is that if we have a constant times a function, what you should do is fix the constant and then differentiate. So we're going to be doing that. I think what we're going to do is we're going to do dVdh here. So what I'm recommending when you're differentiating any function from now on is fix the constant and differentiate. So what this means is that if you were to differentiate, say, 6x squared, kind of what we're taught to do, or the way we think about it, because this is the way we do it, we kind of think of the 2 multiplying the 6 here. But that's not really what happens. What actually happens is you fix the constant and then you differentiate x squared, which is 2x. And it's more like 6 by 2 than 2 by 6. And of course they're the same thing. And so it doesn't matter if you kind of do this. But for later on, it's going to be better to fix the constant and then differentiate. And the constant here is 1/12 pi. So fix the 1/12 pi. And now the derivative of h cubed with respect to h, using the power rule, is you multiply by the power and reduce the power by 1. Now we could simplify this to 1/4 pi h squared, but I'm not too bothered. This is basically saying how the value, if you want to get into it, this is saying how the volume changes with height. It says if you increase, okay, so what it's saying, it's a bit unnatural actually. If you increase the height, say, by 1 meter at this point, this is how much the volume will change by. And when h is small, it's a bit complicated because we've got 2 different types of height going on. What I'd say is when the height is small, down the bottom, changing the height by say 10 centimeters doesn't change the volume that much. Whereas when height gets big, you got height squared, changing the height will have a big increase in volume. Okay, so I'll put the question all together. Well, we're missing one thing. So we have dV/dt, that's a number. We're looking for dH/dt, this is our unknown, and dV/dH we have in terms of h. So actually there's 2 unknowns at the moment, but if we read the question a bit carefully, we know that the height, we're interested in when the height is equal to 1. So this is like a certain, going back to my little picture here, I'm interested in at a certain point, how fast the height is changing. Because obviously when there's more liquid in it, when it's higher up, the height isn't going to be changing so quickly. Okay, so we put h equal to 1 into this, we get 1/12 pi by 3 by 1 squared. I'm just going to keep it simple. 1/12 pi, 3 by 1 squared is 3 by 1, 1/12 pi 3. Okay, I can't do it any longer, so 3 divided by 12 is 1/4, so I have 1/4 pi. That's what dH/dt is. So putting it all together, what I mean by putting it all together is putting this all together. I know that dV/dt is equal to 0.05. dV/dH I found is 1/4 pi times dH/dt, which is what I'm looking for. And you just got a little algebra problem here. Now the way I think of this myself, now there's different things you can do. I mean, I like nice numbers. I'm a mathematician, so I'll show you. Like I would end up with dH/dt. I'd multiply both sides by 4, and I suppose that would be 0.2, which even then I'd call a fifth. And then I divide both sides by pi. So I'd get 1/5 pi, and this is a nice number, no approximation. We'll talk about units. Well, you see, as a mathematician, maybe I wouldn't even care about units. So this isn't necessarily what you're going to be doing. You've got what you're looking for multiplied by 1/4 pi, and you need to get rid of multiplying by 1/4 pi, and the inverse of multiplying by 1/4 pi is dividing by 1/4 pi. And you can just do that on the calculator. Now, if you are rounding, I'd like 4 significant figures, and I like the squiggle to show that you understand that you are rounding. So I have 0.05 divided by 1/4 pi. I suppose I can show you this on the thing. 0.05 divided by 1/4 pi. Now I'm going to take 4 significant figures, so 0.6, That's the first significant figure, second, third, fourth, and you round this last one if necessary, but I don't have to. So 0.6366. And now finally you have to think about units, and this was mentioned in the previous video. The units of dH/dt, it's the rate of change of height with respect to time. It'll be the units of height divided by the units of time. Now, the time mentioned is seconds and the height mentioned is meters, so this is meters per second. And you can write it as m over s, you can write it ms to the minus 1, they're the same thing, because to the power of minus 1 means dividing. Okay, we will go on to the next example. So I got here, air is being pumped into a spherical balloon so that its volume is increasing at a certain rate. So this is the problem we started with. Say there's an air pump and you know that it pumps 100 centimeters cubed per second. The question is, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so let's maybe just do our master equation first. So what are the variables? Volume, radius. Now diameter is here. Now it's funny, I don't know if you remember when I was in school, in primary school they talk about diameter first, but once you don't really use the diameter is natural is radius. So we're going to instead talk about radius, and here it is, and we're talking about when the radius is half the diameter, 25 centimeters. The other thing knocking around, of course, is the time. And we're going to take the most complicated thing and differentiate it with respect to time. So the complicated thing, is it volume, is it radius? Well, using what we said before, volume is a function of radius, so volume is the complicated thing, so differentiate volume with respect to time. So we differentiate, and how we do this, we spread this out, dv dt, and then what we do is we bring in the other variable, which is radius. So you got a dr and dr. Okay. Now what have we got? Right, dv dt is the rate of change of volume with respect to time. That's actually in the question. The volume is increasing at a rate of 100 centimeters cubed per second. So this is no problem. This is 100, and we will put this down here. Dog's barking now, hopefully he keeps quiet. Right, now what's the next thing? So the next thing is there's a formula that's not here, and it is the relationship between volume and radius. So we got volume is equal to 4/3 pi r cubed. And so what we're interested in terms of dv dr is we want to differentiate this. Now again, like I said before, if from now on, when we're differentiating, I want to fix the constant and then differentiate. So fix the 4/3 pi, that's fixing the constant, and then differentiate. And the derivative of r cubed is 3r squared. And what would be nice here is 3 divided by 3 is 1. So this is 4 pi r squared. And this is just something maybe for you to Google. The rate of change of volume with respect to radius is actually equal to the area as a function of radius. That's something for you to think about. Suppose if you have if you think of maybe make a large sphere or ball out of tin foil, how do you increase the volume a little bit? And what is the relationship between the change in volume and the area? But I won't go into that here. Don't have the time so much. But anyway, the dv dr, the derivative of volume with respect to radius, is 4 pi r squared. I will throw that in here at this point. And then dr dt. So is there anything telling us what dr dt is? We have a look around. Dr dt is the rate of change of radius with respect to time. And if we read this, this is the question. How fast is the radius increasing? How fast is the radius changing, in other words? So dr dt is what we're looking for. We're in fairly good nick at the moment, except we've got two unknowns, dr dt and the radius. You can't solve one equation and one unknown, but luckily they said we're interested in this problem at the point where the diameter is 50, which is saying that the radius is 25. So I'm going to substitute r equal to 25 into this. Now I could convert this into meters and do everything in, well actually no I couldn't, because if you look at dV/dt it's at 100 centimeters cubed per second. My advice is that keep all the units the same. If this is centimeters, keep it centimeters. If this is centimeters and this is meters, you're going to have to convert one of them, and converting 100 centimeters cubed is a bit more difficult. It's no such problem here. You've 25 centimeters, 25 centimeters. So I'm substituting in 25 centimeters because it's asking, this is dV/dr, the rate of change of volume with respect to radius, and we're interested in when, at this point when the radius is 25. Now again, if we want, mathematically I get a nice kind of an answer here. It'd be like 100 over 625, that's something like 4 over 25 pi, something like that. Or maybe it's 1 over 25 pi, it doesn't matter. But as an engineer, you're not necessarily as concerned. The numbers in the real world, of course, if you ever were to face a problem like this, wouldn't be so nice as 25 centimeters. So ultimately, you've got a number here that's multiplying what you're looking for, and the inverse of multiplying by this number is dividing. So I'm going to divide both sides by 4 pi 25 squared. If I divide the right hand side by that, I'll be left with dr dt. And so I must divide the other side as well. So I've got 100 divided by 4 pi by 25 squared, which is not actually what I put into the calculator. Look, what a dope. 4 pi by 25 squared. So I'll use 4 significant figures. 0, this is the first significant figure, second, third, fourth. Round this if necessary, no. So 0, 1, 2, 7, 3. And again, the units will be rate of change of radius with respect to time, will be units of radius divided by units of time. The units of radius here are centimeters. So centimeters per second. Okay, this is 2 examples, and we will go on to do one more. So yeah, right. So this one is a bit. There's a bit more to it. Okay. Now this question, I haven't asked a question this tricky in a while, but there's 2 options. Okay. So if we look at the question, and at this stage we're looking for functions. So we've got area, we've got volume, we've got radius, and we've got per second, so we've got time knocking about. And this is more variables than you're used to, which is a problem. Now, I've different things I can do here. So the one thing you could do is, okay, let's look at it as 2 separate problems. Let's look at the area problem and the volume problem separately. And that might be a possibility. So down the bottom, we'll look at it like that. So area, the other thing we must say, okay, we're talking here about a sphere. We need to write down formulas. The area as a function of radius, go into your big tables, is 4 pi r squared. And the volume as a function of radius is, go into your big tables, 4/3 pi r cubed. Okay. Well, that's something. So maybe we can look at this separately and see what happens. So, and this is how I used to do it, but I think the second thing is a bit better because it shows you what to do if you pick the wrong function to differentiate time with respect to. So that's good. So the other option that I'm not going to go through is do two separate problems. So do area and radius. Now you're not going to differentiate area with respect to volume, or volume with respect to area. It's possible, but it's very messy actually. Now you could come up with something on your own if you had a thought. You could think of them as both as functions of radius, and you could say that radius was the parameter. That actually would be kind of a clever thing to do. You could look at, so something as complicated as dV dA, which doesn't necessarily make sense to us. It's the rate of change of volume with respect to area. If the area changes by 1, how does the volume change? Well, you could see these both as parametric functions, and you could do, like the previous section, dV/dr divided by dA/dr. That is actually a possibility. That's, I think, a third possibility that I won't look at. So the r here is a parameter. So the other option that is to do them separately, do area with radius. So you do dA, area being more complicated than radius, differentiate it with respect to time. Spread this thing out, dA dt, and then just throw in the other variable, which is radius. Now, how is this going to work? Well, we'll see that in a minute. Then the other one is dV dt. Oh yeah, sorry, volume and radius. And volume is more complicated than radius, so differentiate the complicated thing with respect to time. Spread it out as dV dt. And then throw in the other variable, which is dr. Now, let's see. This is an option. You kind of break it into two. Okay, now what do we know? What do we not know? The first thing it says, the surface area of this sphere is increasing at a constant rate of 500. So that means that you know dA dt. Okay. Oh, okay. Find the rate of change. Now, dA dr, that's a function of r. You're going to differentiate that, and you know the radius, so actually you know this. And what that means is, if you know the both of these, you can find the two of these afterwards. So this can be found. That means that dr dt can be found from this. dV/dr, just differentiate this with respect to radius, substitute in 20. So this can be found. And you end up, you can find dV dt. Is that the question? Yes. Find the rate of increase of the volume. Find the rate of change of the volume, dV dt. So that's one option. And that's probably the smarter thing to do as such. I'm going to do it a different way. So this is going to be just a bit kind of braver. What we're going to do is we're going to say we're looking for the rate of increase of the volume, the rate of change of volume. I'm going to write dV dt. That's what I want to find. And I think what I'm going to do is I'm going to spread this out. So this is a double chain rule. I think we're going to imagine, well, let's see. Well, I'm not going to imagine anything. Let's see. Yeah, so actually what we're doing is we're going to say that volume is a function of radius. Radius is a function of area, and area is a function of time. So it's like a double chain rule. So this is a chain rule. This is differentiated outside by the derivative of the inside, but the inside needs a chain rule as well. And this is where treating these things as fractions, you can do it so far. So I need to start throwing down dAs and dRs. And I need to be careful. If I put dr here and dr here, I've got dA and that doesn't tell me anything. And if you can do that, like dA is 1, but it won't actually work out. So if I put dr here, I have to put dr here. And I don't want to put dA here because I don't know how to find dV/dA. So I'm going to put dr here. I can't put it here. I'm going to put dr here. And then I'm going to put the other thing, the area, dA dt and dA. Okay, and this is legitimate. Now, it might be easier to do it this way, but the reason I show you this is for the next bit. So dV/dr is actually no problem to us. We're going to find that. dA dt is actually in the question, as we'll see in a moment. The problem is dr dA. We don't know how to do dr dA, but we showed, or really we said in the theory lecture that dr dA, if you want, you can flip them around, it's 1 over. So dr dA is 1 over dA dr, and dA dr is something that we can find. And the dA dt is still sitting here. And here we actually see, well, we see nothing really. Okay. Okay, we're game ball now, because dV/dr we can find, differentiate the volume with respect to radius, fix the constant, 4/3 pi. Derivative of r cubed is 3r squared. 1 over dA dr, differentiate this again, fix the constant 4 pi, times the derivative of r squared is 2r. and dA dt is hopefully in the question. The surface area of the sphere is increasing at this rate. The rate of change of area with respect to time is 500. And all we have to do now is just throw in that the radius is equal to 20. So I'm going to say I'm going to evaluate this at radius equal to 20. And now there's all kinds of simplifications I could look at here, but I'm not too bothered. It's going to bang in all the numbers. Well, you can bang in all the numbers. Maybe I should do a little bit better. So to do a little bit better, I can do 4 pi divided by 4 pi is 1. 3 divided by 3 is 1. And all I'm actually left with is r squared divided by 2r. Which is actually equal to r over 2. So just to be clear, 4 pi divided by 4 pi, gone. 3 divided by 3, gone. I'm left with r squared over 2r. Times 500, and I'm going to bang in r equal to 20 into this. And I end up with 20 squared over 2 times 20. And we'll bang this into the calculator and see what pops out. Of course, if you bang it in there, you'll get the same thing. 20 squared divided by 2 by 20, which of course is 40, times 500, and it comes out as 5,000. And again, check the units. Rate of change of volume respect time, the units of volume divided by units of time. Units of volume, here, if it's all centimeters, the volume is centimeters cubed, and the time is second. You can think, if you want, a little bit about the relationship between all these numbers, but ultimately this is the answer. This is what we're looking for. Thank you.